Okay, the command here is pretty simple. It's just ANOVA, the dependent variable miss, followed by the independent variable feedback. All right, so the first thing we'll look at is the R squared. And we have an R squared of 0.4198. Remember that R squared is simply the amount of variability in the dependent variable that can be explained by the independent variable. Okay, and we can write this out as a percentage. So you might say that 41.98% of the variability in missed baskets can be accounted for by praise type. Which is quite a lot. So this is, about 40% of the variability in the number of missed baskets can be explained by the type of praise received. And if you were a basketball coach, that would be a pretty significant amount. If you know that the type of praise or criticism that you provide can predict about 41% of the missed baskets, you'll want to know what type of praise or criticism is best. Right, and next with the ANOVA table, we have a model line, a feedback line, and a residual line. Because this is the one-way ANOVA, the model line and feedback line are exactly the same, but it's best to get in the habit of reporting the feedback line here. Once we get into factorial ANOVA and have multiple independent variables, you'll start to see how the model line will differ from each factor. Remember that the feedback line here is essentially explaining the variability in number of missed baskets that's accounted for by feedback, and the residual line is the variability unaccounted for. So just variability in number of missed baskets that can't be explained by feedback type. The degrees of freedom for this model are 2 and 27. Remember that degrees of freedom for this factor is simply the number of levels minus 1. And the degrees of freedom error is simply the total number of observations, which can be found here, minus the number of levels in your factor. And finally, we have an F statistic of 9.77 and a p-value of 0.0006. So this means that our Omnibus ANOVA is significant. Now, with a significant ANOVA with 3 levels of an independent variable, we can't actually know where that significant difference is. Okay, so we have 3 means that this ANOVA is comparing here, and we need to determine which means are significantly different from each other. It could be the case that only 2 means are significantly different from each other, or it could be that all 3 are significantly different. We won't know until we do post hoc analyses or post hoc comparisons. Now, let's say this p-value was non-significant. If it was greater than 0.05, we would really just stop here. If the p-value is non-significant, that essentially means that there is no significant difference between the 3 means. We would fail to reject that null hypothesis. But again, because we have a significant p-value, we know that there's a real mean difference somewhere. We just need to assess where that is. But before we do that, let's go ahead and assess the assumption of homogeneity of variance. Remember that one of the assumptions of ANOVA is that we have equal variability in our dependent variable at all levels of our independent variable. And we'll do this using Levine's test. And Levine's test, the command is robvar, that stands for robust variance. The command is robvar, the dv miss, by the independent variable feedback. Now let's recall the null hypothesis for Levine's test. This simply states that the standard deviation for praise type 1 equals standard deviation for 2 equals the standard deviation for group 3. Okay? So the null hypothesis simply states that the standard deviations for all groups are equal, which means if we fail to reject the null hypothesis, we have met the assumption of equal variability. Right? And with this output, we only need to interpret this top line, and really we just need to interpret the p-value here. With these data, the p-value is, for Levine's test, is 0.62, which is well above our cutoff of 0.05. And in this case, again, if we fail to reject the null hypothesis, it's a good thing. So this essentially is saying we have met the assumption of homogeneity of variance. So let's talk a little bit more about mean comparisons before we get into demonstrating it in stata.